In this video, we're going to look at how to develop and determine a few points on our moment axial load interaction diagram with a column with multiple layers of steel, so more than 2 layers. So here you can see our 30-inch deep and 20-inch wide column with 4 different layers of steel. So the first thing that we'll do is we'll define our layers. So we'll call the top layer 1, middle layer 2, the bottom middle layer 3, and the very lower layer 4. Then we'll need to determine our AS1, which is 4 number 9 bars, so 4 square inches, our AS2, 2 square inches, our AS3, 2 square inches, and our AS4, 4 square inches. We can also then find our Ds. So our D1, 2.5 inches from the top, our D2, 10 inches from the top, our D3, 20 inches from the top, and our D4, 27.5 inches from the top. 30 minus 2.5 is 27.5. The last thing that we'll need here is our beta. So for 5 KSI concrete, our beta 1 is equal to 0.85 minus 0.05, 5 KSI, which is F prime C, minus 4 KSI is going to equal 0.8, and this is greater than 0.65, so our beta 1 is 0.8. So the first point that we're going to find is the tension controlled point. And we can remember that the tension controlled point is the point at which our extreme tension steel or furthest down layer of steel has a strain equal to 0.005. So by similar triangles, so that triangle, this triangle, we know that 0.003 over C equals 0.005 over D4 minus C. So we can rearrange this and solve for C, and we'll have our C is equal to our D4 times 0.003 divided by 0.005 plus 0.003. So if we plug in our values here, we'll have 27.5 times 3/8 is equal to our C of 10.3 inches. We can also find our A from this, and we'll remember that our A is equal to beta 1C. So for us, 0.8 times 10.3, which will give us an A equal to 8.25 inches. With our C, we can now calculate the steel stress in each one of our layers of steel. And we can remember that wherever our stress is greater than 60 KSI, we'll use our yield stress. All right, so let's go through and calculate the stress in each layer. So our first layer, 0.003 times 29,000 KSI, our stiffness, times our C, which is 10.3 minus 2.5 over 10.3 is equal to 65.9. So we'll use 60 KSI because we've yielded. Our next layer, 0.003, 29,000 KSI, and then 10.3 minus 10 over 10.3 is going to be equal to 0.64 KSI. So we haven't yielded there. So we have our strain in our second layer of steel, or stress in the second layer of steel. Third layer of steel, 0.003, 29,000 KSI. And then 20 inches minus 10.3 over 10.3 is going to give us 81.7 KSI. So we know this layer of steel has yielded. So we have the stress in our third layer of steel. And then our final layer of steel, we can assume is going to have, or we know is going to have a strain of 0.005. So we can just skip our calculation here and say that our FS4 is equal to 60 KSI. And this is because we're setting it equal to tension controlled, which is past yield. So now we have our stress in each layer of steel, and we have our C and we have our A to move forward. We're now ready to calculate all of our force components. So we'll have our 4 layers of steel and we'll have our concrete force component. So first, our first layer of steel, we found that our top steel yielded. So we have our 4 square inches of steel times our 60 KSI is going to be equal to 240 kips. Next, our layer of concrete, 0.85 times F prime C times beta 1 times C, and then times our B, which is 20 inches, will give us a force in the concrete of 701.3 kips. Then our second layer of steel, we have 2 square inches, and in that second layer we had 2.64 KSI stress. So we'll have 5.28 kips of force. Our third layer, we have 2 square inches of yielded steel and tension to give us 120 kips. And finally, our fourth layer, we have 4 square inches of yielded steel and tension to give us 240 kips. So we have our 4 force components. When we want to find our axial load, PN, we just sum all of our components. And we're going to do our compression force is positive. And our tension force is negative. And if we do this, we will find our force here to be 586.5 kips compression. Next, we can calculate all of our lever arms. So first, we'll find the lever arm to our top steel. So H over 2, 15 inches minus 2.5 inches is 12.5 inches. So our lever arm 1. Next, the lever arm to the center of our compression block. So 15 inches minus our A over 2, so 8.25 over 2 is going to give us a lever arm of 10.9. Next, our lever arm to our second layer of steel, 15 inches minus 10 inches equals 5 inches. Our distance to third layer steel, 20 inches minus 15 inches equals 5 inches. And then finally, 27.5 inches minus 15 inches is 12.5 inches. So if we were calculating additional points, our steel lever arms would all remain the same because we are calculating our moment about the plastic neutral axis. So the location of the steel layers doesn't change. The only number that we would have to update is our YCC. the distance from the plastic neutral axis to the centroid of our compression block. So we could update that every time we changed our neutral axis depth. So we can use these lever arms then moving forward to calculate our moment. We can now calculate our moment. So our moment is going to be equal to the summation of all of our lever arms times our forces. So our first combination, 12.5 inches. For our top layer of steel, 12.5 inches times 240 kips, plus our second lever arm, which is 10.9 inches, times 701.3 kips, plus our third lever arm, 5 inches, times 5.3 kips, plus 5 inches, times 120 kips. And then our last component is 12.5 inches times 240 kips. So this will give us an MN equal to 14,252 kip inches. So this would give us our moment, and then we remember our axial force from our previous slide of 586.5 kips. So we have our point for our diagram for tension controlled. The next point that we're going to find is our pure flexure point. And we're going to find it using the trial and error method or iterative method, where we first guess a C, then calculate all our stresses and forces and our moment, and we see if the summation of our forces equals 0 or not. And if the sum of our forces does equal 0, then we know we got our C right, and if it doesn't, then we need to try another C. So our first guess is going to be C equal to 5 inches. So for a C equal to 5 inches, we'll have an A equal to beta 1C, so 0.8 times 5 is going to equal 4 inches. So we're first going to calculate the stress in all of our layers of steel with our guessed C. We can see that our C is falling, in this case, between our first and second layers. So our top layer is going to be in compression, and the next layers are going to be in tension. So you can see that's how I set up our equations here. All right, so finding all of our layers of steel, and remembering that if we get a stress higher than 60 KSI, we need to just use our yield stress. So 0.003 times 29,000 KSI times our C minus 2.5 over, 5, our C, is going to be equal to an FS1 of 43.5 KSI. Our second layer is steel, 0.003 times 29,000 KSI times 10 minus 5 over 5 is equal to 87 KSI. So we know that our second layer of steel is yielded. So because our second layer of steel is yielded, and all of the other layers of steel are going to have higher strains than the second layer, we know that our third layer and fourth layer of steel have also yielded. So now we have our stresses in all of our layers of steel, and we have our guess for C. Next, what we'll do is we'll use all the stresses that we calculated and our C to find all of our forces. So the force component in our top layer of steel is our total area of steel times the stress in that layer of steel, 43.5 KSI. We saw it was in compression, which is why I have a compression out front. So this will be 174 kips. Our concrete is going to contribute as well, so 0.85 times 5 KSI times 0.8 times 5 inches times 20 inches, which is our B, is going to equal 340 kips. Our TS2 is just 2 square inches times 60 KSI were yielded, so 120 kips. Our third layer of steel also has 2 square inches. It's also yielded, so it's also 120 kips. And then finally, our last layer of steel, we have 4 number 9 bars, also yielded, so we're at 240 kips. So we can find our P then equal to 174 plus 340 minus 120 minus 120 minus 240, and this will give us a P of 34 kips. We can see that our 34 kips is not equal to 0, so we need to try another C. But we can see that our 34 kips is in compression, so in our next guess, we'll need to decrease our compression force. To decrease our compression force, we will decrease our C. So we can see we need to decrease compression. So we'll try decreasing C. We're pretty close to 0 though, so we're going to try just decreasing our C just a little bit. So we're going to try decreasing our C a little bit to 4.75. And when we decrease our C, we're going to need to recalculate all of our stresses again. So we're going to recalculate our compression stress in our top layer. So 0.003 times 29,000 times 4.75 minus 2.5 over 4.75, which will give us a stress of 41.2 KSI. So we know that at a C of 5, our second, third, and fourth layers all yielded. So when we move up our neutral axis a little bit to 4.75, they're still going to be yielded. So you could check using our expression again for FS2 and FS3 and FS4, but you'll find that all the layers still yield. So with our C and with our stresses, we can calculate all of our forces just like we did before. So we'll have AS1, 4 square inches, times 41.2 KSI to give us 164.8 kips. Then we'll have 0.85 times 5 KSI concrete times beta 1.8 times our C, which is 4.75, times B, 20 inches, is going to give us a C sub C of 323 kips. Then all these will be the same as last time, but 2 square inches yielded 120 kips, 2 square inches yielded 120 kips, and 4 square inches yielded 240 kips. So then we can find our P, and our PN is going to be 164.8 plus 323 minus 120 minus 120 minus 240, and this will give us a Pn equal to 7.8 kips. So you can see we're pretty close to 0, so I'm not going to iterate anymore, but you could try iterating again and maybe try 4.7 and see if you could get to 0. You could also use a solver in Excel and calculate the exact C if you wanted. So next we need to find our moment, and we'll do this by taking all of our lever arms times our forces and adding them together. All of our steel lever arms are going to remain the same from our previous steps. As I said, we're summing our moments about our plastic neutral axis, so our steel layers don't change. Our concrete lever arm does change, so we need to recalculate that quickly. So I have 15 inches minus A, which is 0.8 times 4.75 divided by 2. So we'll get 13.1 as our lever arm here. And then we can plug all these values into our moment expression. But we'll need to think about how to combine them first. So we can draw our force diagram. So we have our top layer of steel in compression to the right, or in compression. So top layer steel in compression. Then we have our concrete force in compression. We have our second layer steel in tension, our third layer steel in tension, and our fourth layer steel in tension. So remember, we're summing our moments about our plastic neutral axis. So you can see that all of, or 4 of the moments are going to be in the same direction, and we have 1 moment that's going to be in the opposite direction. So when we're combining them, we just need to make sure that we subtract off the second layer steel moment. So we'll have our Mn equal to 12.5 times 164.8 kips plus 13.1 times 323 kips. So minus, because we're looking at this next term here. So minus 5 inches times 120 kips. We're back to positive because we're going in the same direction here for the third layer. So plus 5 inches times 120 kips, and then plus 12.5 inches times 240 kips. So this will give us an Mn equal to 9,292 kip inches. So this is our final moment. And remember, we were looking for a pure moment, pure bending. So our P was about equal to 0 kips. Doing multiple layers of steel or finding the capacity of columns with multiple layers of steel can be burdensome, as we've seen. So it can be advantageous to set up an Excel sheet to solve for these things automatically.